All right, let's do a couple of multi-part y-axis kinematic problems. This one actually involves both the y and the x-axis. It's a traditional Looney Tunes issue. Wile E. Coyote is trying to drop an anvil to take out Roadrunner because, you know, crazy Wile E. Coyote, he always thinks he should eat Roadrunner. So he drops an anvil off a cliff that is 52 meters high. Now, Roadrunner is coming by 95 meters per second because it's a Roadrunner. He can sure pick up a lot of speed. So Wile E. Coyote realizes, I better drop this anvil well in advance. 200, while he's 250 meters back is what he figures he's going to do. And the question here is, does he actually get Roadrunner? So if you think through the physics of this problem, we want the anvil and the Roadrunner to occupy the exact same time and space. If we're Wile E. Coyote, if we're Roadrunner fans, we'd prefer that not to happen. So here's one way to do it. Let's solve for how long it takes the anvil to fall and hit the ground. Then use that time to see how far Roadrunner travels and set it up as a comparison problem. Because if Roadrunner goes further than 250 meters in the amount of time it takes for the anvil to fall, then Roadrunner is able to escape underneath. On the other hand, if Roadrunner is almost right around 250 meters, then he's probably going to get hit. So if the amount of time it takes to fall, Roadrunner covers 250 meters, he's probably going to get hit. Or Wile E. Coyote might have dropped it too early. If the anvil falls and Roadrunner has only covered, let's say, 200 meters in that amount of time, then he's still going to be safe. The anvil will land in front of him. So let's start out solving for how long it will take the anvil to fall. All right, so I picked my positives and negatives here. I said everything that goes up is positive, down is negative, left is positive, and right is negative, just according to how my pictures are drawn. I'm also picking my zero, and then because of the positive and negative, the 0 point is going to be the ground, and I'm purposefully reversing up what I did in the y-axis compared to on the last video with the Empire State Building, just to show you a different way to solve here. So I'm saying the ground is 0 and down is negative. Acceleration of gravity goes down, that's what's happening here, so negative 9.81, and the anvil starts out 52 meters up in the air and falls down to 0, right? So that's just choosing a different positive and negative direction here, and I'm solving for time, and since it was dropped, initial velocity was 0. Pick an equation, solve for how long. I want to pause here in substituting in and point out this middle term here is going to cancel out because of the 0 initial velocity. But do not count on that always occurring and just automatically discount this middle term. You will have initial velocities at times, and whenever you have initial velocities, this becomes a quadratic that is going to require the quadratic equation. But since there is no middle term, it goes away, making this relatively easy. I come out with 3.26 seconds. Significant figures gets me to 3.3 seconds. Now I'm going to use the unrounded time purposefully now to solve for how far Roadrunner is going to end up getting. By the way, I'm only writing down the 3.26. I would much prefer you use the entire number stored in your calculator, 3.25598, so forth and so on, and only round for significant figures at the very, very end. So let's set up how far Roadrunner is going to get. Now he's going at a constant velocity, not accelerating, and here's how long he has to run. And you can see, as always, after substituting into the constant velocity equation, because that's what Roadrunner's doing, he's not accelerating, just going along at 95 meters per second. Roadrunner, of course, makes it underneath the anvil before it falls. More than likely, the cliff will break here in a minute for Wile E. Coyote, because that seems to be what happens with his luck. All right, a standard rocket problem can be worked in either 2 or 3 pieces if you're looking for maximum height and how long will it take to get all the way up and land. So I have a standard kind of model rocket, bottle rocket kind of thing. It takes off with an acceleration of 7.9 meters per second squared, and the engine lasts for 19 seconds. And during that time, it is accelerating upwards, and so I have an acceleration piece upwards. Then my next piece here, I lose engine power, and so I coast upwards to my maximum height, losing velocity at all time. And this is subject to gravity. Acceleration equals negative 9.81, and that's assuming that I'm calling up positive and down negative, as I have indicated over here. Then I reach my maximum height, where the velocity, right, at the maximum height is going to be 0, and I have my second piece, where we start falling back down to Earth, neglecting air friction once again, all the way back down, and that's subject to gravity as well at negative 9.81 meters per second squared. And I'm looking for, in this problem, the maximum height, and also I'm looking for the how long it will take before it lands back down, the total time. Now, just thinking through this, for me to be able to solve for maximum height in this blue piece right here, I'm going to actually have to find out a few other things. I know the acceleration of gravity, negative 9.81 in that piece. That's the acceleration. But I don't know where this piece starts from, x, right here, right? Nor do I know what the initial velocity of this piece is. If I knew those two things, this would be just like someone throwing a ball up in the air. A very simple problem, gravity pulling it down, initial velocity going up, solve for the maximum height. Now, where I get those two pieces from is the acceleration piece of the rocket. So here's going to be our goal. We want to solve for these two things. We want to solve in red for our final velocity, right, which, by the way, becomes the initial velocity of the next piece, and solve for our final position becomes initial position, and solve for our final velocity, which will become the initial velocity of the next piece. And you'll see these in a lot of physics problems where you solve for one thing in one piece and it carries over into the next piece. So let's go ahead and start doing that. All right, so I wrote down all my variables that I know and the two things that I'm looking for. I'm looking for final velocity. I'm looking for final height and the accelerating up piece there in red in my picture. I'm going to start out by solving for the final position in this red piece. So let's pick a kinematic equation. Now, if you're having trouble still picking the right kinematic equation, that's okay. My piece of advice to you would be do process of elimination. You can go about it one of two ways. You can look at it and say, what don't I have? And the answer here is you do not have final velocity, so you must pick the equation that doesn't have final velocity in it. Or you can look at your equations and just go through them. Say, okay, I have acceleration. Does this equation have acceleration? Yes. I have initial position. Does this equation have initial position? Yes. I'm looking for final position. Does this equation have final position? So on and so forth. And eliminate equations all the way down until you get to the right one. So now we just need to chug through this equation. Come out with a final height for this rocket because, I mean, it was accelerating for 19 seconds. That's actually very, very impressive for a model rocket. Just about 1.5 kilometers, 1,425.95 meters, and I'm not rounding that just yet. I'm going to round at the very, very end for significant figures. Now I need to find the final velocity that it was at, so let's pick a different kinematic equation. A piece of advice: try not to use kinematic equations inside the same pieces that involve numbers you've already solved for. While it would be legal to pick a kinematic equation that involves final position now, I prefer to just use the variables that we were given to start out with. All right, and that lets me solve all the way down. I find the final velocity of this rocket in this piece, the accelerating up piece, to be 150.1 meters per second. So now I know the final position in the acceleration piece and the final velocity in the acceleration piece. And now we're able to go into the next piece where the acceleration changes. The engine runs out of fuel. So now we aren't actually accelerating upwards anymore. We're technically in free fall. Gravity is decelerating it down at negative 9.81 meters per second squared. So we're losing velocity. But the final position in this piece becomes the initial position in the next piece, and the final velocity in the acceleration piece becomes the initial velocity as we start slowing down. So let's write down the variables that we already know and what we're looking for, which is going to be the maximum height, and then start solving. All right, so we were able to carry over our variables in here, and also remember the velocity at the maximum height is 0, and so let's solve for at what y position do we have a 0 velocity all the way up here at the maximum height. And you come out with significant figures because you only have two sig figs and the initially given variables. Sig figs only come from initially given variables, I should say that as well. Maximum height of 2,600 meters, so 2.6 kilometers. That's up a little high there. We might have some problems with other planes flying by, but that would be the max height of this rocket. Now, I am not going to solve for you right now that I think about it how long it will take before it's going to land back on the ground. In fact, I'm going to let you solve for that. If you can come in on our next class period with how long it will take for the rocket to get all the way up and all the way back down, then I'll give you a few bonus points, maybe 1 or 2 bonus points on this homework assignment. So you've already got the time for this chunk. Figure out the other times. And I'll see you next class period.